we are going to this wonderful theory of Seldovich. But as I told you, in this theory, there is no hydrodynamics except the one due to the conservation of mass in one dimension that tell you simply this relation. That's all. That's the whole hydrodynamics we are going to have in this theory. But in that sense, rho u is constant. So this again, you know, this now the flame is on the other side. The unburned gas is coming from the left, and the burned gas is going out from the right, and I sit here on the flame. That's, but what is important is rho u is constant. That's all. And now here are the equations, because you took out the pressure effects in the conservation of energy. So the conservation of energy, I have neglected the viscous effect also, and I keep only the conduction effect that you have here. And now this is rho u, which is equal to m, is an unknown. You do not know what is going to be the flame velocity. You are looking, you want to solve the problem to obtain the flame velocity in terms of the properties of the initial mixture, unburned mixture. This is the objective. Can I obtain a relation between the flame velocity and the initial mixture, density, temperature, and so on? So the problem you have to solve is simple. No, it's not simple. It's a very difficult problem. But it is expressed in very simple terms. And this is what I enjoy in theories, to have something expressed in a simple term, but the solution of which is very complicated. It's very, as you said, instructive and so on. So the equation you have to solve are two equations, quite similar for the temperature and for the mass fraction of each species. Here you have a picture of the profile of in a real flame, where you have many species. Okay? And in fact, in this problem that you have to solve, you have boundary condition. And the boundary condition is such that there is no reaction rate neither in the burned gas. You assume that everything is burned, but also in the fresh mixture, because the fresh mixture, the unburned mixture, is frozen, completely frozen, because the temperature is too low. And the temperature being too low, there is no reaction. So these are the boundary conditions. And then the initial temperature, you know what it is, Tu, and the concentration, YIU, is given. This is a property of the initial mixture you are considering. These are given quantity. So, but now, to be honest, you do not have the burned gas temperature. We will find it immediately. But what you know is that you know exactly the the mass fraction of each species, because either you assume that the some chemical reaction are in equilibrium, so you have a relation between in that case. But forget about the detail, because I am going to be even simpler than that. But this is a general formulation that you have when you want to solve a flame by computer, knowing all the kinetics, chemical kinetics. You have to solve this problem. In this problem, you know, in the equation, you have a term that you are looking for. This is called an eigenvalue problem, because the problem is set in such a way that the equations are known, except that in this equation, you have an unknown that you have to find. And this is, you will see, this is a subtle point I am going to discuss later on simple cases, simplest case, because it's the same and it's difficult to understand if I am not going. No, the simplest case I am going to consider is the one considered by Zeldovich, was it when 25, something like that. Because the problem of what is the flame speed was open since one century, almost, before him. People, you know, say words and words, but no. It is not quite right. There is a man, but I have to go further to tell you some historical point. So let me consider just one irreversible reaction governed by the Arrhenius law. I did not write here the Arrhenius law. It should be here. And irreversible. It's a simple thing. You can, and then you liberate heat, and QM is the heat, which is QR, is the heat liberated by the unit mass of initial mixture, small q. This is by unit mass. Big Q is every reaction liberate big Q. So we can forget about this. QR is energy release per unit mass of R. That's all. Okay, here are the equations. And here are the Arrhenius law. This you have this Arrhenius law. And now I leave to you a small exercise, purely algebraic, no difficulty, is to show that that the reaction rate here, explained here, this is a burn reaction rate. The collision time is the same. This is the collision time in the fresh mixture. This is given. You can use this to introduce the term, the reaction rate. This is what we call the reaction rate in the burned gases. To be more specific, is the reaction rate at the temperature of the burned gas. Because in the burned gas, there is no reaction. But there is no reaction because there is nothing to burn. but the rate is still there. So you have a reaction rate, which is given, that I have written here. So this is reaction rate. So you divide, and it is interesting. This is a simple exercise to show that this ratio here is given by an exponential law where this beta is the activation energy relative to the burn gas, 1 minus Tu over Tb, and this is activation energy. And the theta that I have here, it is the reduced energy, which is the temperature minus the unburned temperature divided by the burn gas temperature minus the unburned temperature, so that this is going to vary between 0 and 1. And in fact, if I use the reduced mass fraction, it is also going to vary from 1 to 0. Okay? That's and now you are going a step further. Assume that the Lewis number is unity. Here, I have written the equation in the dimensional form, introducing the reduced mass fraction of the reactant, which is the mass fraction divided by the initial mass fraction. The mixture that you have initially is you have an inert gas in it and a reactive species that decomposed. You know, and YU is the mass fraction in the initial mixture. So you divide that. This gives you this psi going to 0, 1, and the reduced temperature varies also between 0 and 1. So it should be, but it's a fresh mixture. This is the flame is propagating. Wait a minute. From left. Oh yes, the flame is propagating from the left to right. So at in the something wrong? No. The flame is propagating from right to left. So at the in x going to minus infinity, I am in the fresh mixture. Theta equals 0, t equals tu, and psi equals 1. And on the other side, so I have the flame propagates from right to left. And now on the burn gas side, you have just the complementary, theta equals 1, psi equals 0. Yeah. Now, it's clear that the simplest problem to solve is with the Lewis number equal to 1. What is the Lewis number? Is the ratio of the two diffusivities that you have here. If the diffusivity are the same, the equations are the same. And so, because of the boundary condition, psi equals 1 minus theta. That's all. You end up with only one equation to solve, which is written here for theta. And because now, in the reaction rate, you have replaced psi here by 1 minus theta. So this is this term, the nonlinear term. You have the rho here, but you will see it does not play any role. You will see why. And here you have the expression in terms of theta. This reaction term is a nonlinear function of theta. See, it's highly nonlinear. This makes the problem difficult to solve. Okay? And now the genius of Zeldovich was to invent what now is called an asymptotic theory. I have to be frank with you. From the pure mathematical point of view, the asymptotic theory are not, let's say, the pure mathematicians, pure one, say that there is no proof of the relevance of the solution. It's clear that it is proved. The relevance is proved by comparing with experiment and numerics. But the asymptotic methods are methods that are not recognized by pure math. Pure math, I say, this man who but applied math people use that now every time, everywhere. Okay, now this was the genius of Zeldovich. He said, okay, the problem is nonlinear. Let me push the nonlinearity to become not up to the end. Let's say the highest nonlinearity I can have. Where is coming from the nonlinearity? The nonlinearity is coming from this exponential here. And if I plot here, here it's better. This is, I have written the radius. W prime theta is the reduced mass is a reduced reaction rate I have here. And you notice that this Tb over T disappear here. Why? Because when theta, when beta goes to infinity, if 1 over minus theta is not small, this exponential is going to 0. So you should, when you want to keep the reaction rate, you have to consider very small, very teeny range of temperature close to 1. This, you see, take this, and you are going to tell me, yes, but close to 1, theta is also going to 1. But this is linear. But the nonlinear term here is going very quickly to 0 if you put beta going to infinity and keep 1 over theta non-zero. If it is 0, you have. So the idea, and this is a wonderful idea, before to enter in the technical aspect, which is simple, in fact, by the way, is look to this reduced expression double prime theta in terms of theta. Yes, here is the W prime that you have, okay? If consider term in which theta is not too close to 1. We will discuss what does that mean later. Let's beta go into infinity, 0. So the reaction rate is 0 everywhere in theta, except when theta, stupid. So it's not necessary to develop formalism to understand that. In the paper of Zeldovich was 6 pages. 6 pages. And let me tell you, this was in 38, 39. His mentor was Frank Kamenetsky. It was another Russian man. And one has to wait the 70s to have the following order developed regularly by people. So this means that people need not understand between this analysis during 30 years, especially the combustion community, because the combustion community was stuck with the chemistry. And the chemistry, as I will explain to you, is not useful to understand the mechanism. It is useful to have detailed things, to have how many polluant I have in the burn gas. You have to go to the detailed chemistry. But to understand how the flame propagates, it's not necessary. And this is something that the combustion community took a long time to understand. Because Zeldovich was not only working in combustion. He did a lot of things in cosmology and so on. He was a genius. So now let's go to understand what is the asymptotic method. What is it? So I have plotted here this reduced term in form of theta. When theta is not close to 1, it is 0. It is non-zero close to 1, but it becomes again 0 because of this term. When I am equal to 1, when theta equal to 1. So in fact, the theta is located. The reaction rate is located in a very thin zone close to the burned gas in terms of the temperature. And now, what is calling, and now why this term is not playing any role? It is simply because now you are going to consider beta 1 minus theta afford unity inside the reaction zone. And this tells you what is the asymptotic. You choose the reduced temperature close to 1, such that beta 1 minus theta equal unity when beta goes to infinity. So this means that when beta goes to infinity, the thickness of the reaction zone is going to be thin, 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 and thin. Don't worry. You solve the problem like that. Okay? This is the spirit of what is called, in applied math, a distinguished limit. You take a limit of a parameter going to 0 or infinity, depending on what, and then you take a variable which, in order of magnitude, is related to this parameters going to 0 or infinity. Here it is infinity. Okay? Okay. So you have a thin zone, and if the zone is thin, this term here is not going to play any role. This is, no, excuse me. This term here, TB over T, because T is so close to TB that this is close to 1. And the only term of all unity that you have to keep is beta 1 minus theta. Escape. Do you understand that? This is important. If you have a problem to understand that, let me know. It's not a simple thing. It's a wonderful thing, but it is not simple. Asymptotic methods are not simple. And now the disaster with the asymptotic method is when the applied math took in hand this asymptotic. They put a lot of formalism everywhere that you do not understand anything more. But Zeldovich, if you look to the paper, there is no formalism. So if you do that, you have to solve the problem here, where in fact now I have take out the factor T over TB. This is my I did not write. Where is the reduced equation? Okay, okay. Now, okay, this now is a reduced reaction. Excuse me. This is a okay. This is a reduced reaction rate, and you know you can use an order of reaction which is not unity. You can put n here. That does not change. Will not change the analysis. It changes the result by a number, but not the analysis. But this I used what we call order 1 reaction. That's the simplest thing. This is the definition of W prime, which is here, and W prime is here. Now you have to solve this problem. So it's clear that you have two zones in the flame. You have a large preheated zone where the temperatures vary strongly, where there is no reaction. And you have a thin zone where you have the reaction. But if in this zone I had to solve the full problem, I am lost. The key point is that you understand very well that in the preheated zone, the problem is linear. Now, you are going to solve it. Here is the solution. It's an exponential decay from the high temperature to the random. There is a subtlety here that you use that at x equals 0, which is going to be here. The temperature is a burn gas temperature, because in this equation here, it is an order 1 thing. So you take out the difference 1 over beta. And so you put here this exponential here. You say that here in this, you put 0, the origin is in the reaction zone. So you put here the burn gas temperature. And the burn gas temperature, it's easy to obtain by balancing mass and Y and T, and so it's clear. So you know it is like that. Now, it's clear now that you have the expression of the profile of temperature written here, where the origin is here, and it is written here. And now you see that the thickness is the inverse of m divided by rho Td. And now you are going to use another approximation, is that rho D is constant. Rho dt is constant. You are going to use this. Is easy to remove, but for my lesson here, let's say that it is a constant. So no problem. This is why you have solved this equation. Now, how to solve the problem? I solve the problem in what is called in the asymptotic method the external solution. Now you have to solve in the internal solution, the small one. This is a key point. But what to do? Assume that I know how to solve in the inner zone. What I have to do for the next step is just to say that the heat flux that is coming in the preheat zone is equal to the heat flux which is getting out from the inner zone. I will use continuity of the flux. Okay? This is a basic idea. Not basic idea. Now, you have to solve the inner problem. And if the inner problem is as complicated, no, why I do that? Okay. No, okay. If the inner problem is all as complicated as this one, from when you start, the full problem, you did not gain anything. So the only hope is that the problem simplify not only in the preheated zone, but simplify in a different way in the reaction zone. And this was and this is what is going to happen. Donc, and then if assume that you solve, and then you match, you are going to match the solution, outer and inner solution. This is classical in boundary theory. For example, boundary layer, maybe some of you know some boundary layer theory. It's a complicated thing. Huh? Okay. Now, let me go to the inner problem. How can you solve the inner problem? You compare to know why you can solve the inner problem is, let me give you just the result, is that the term, convective term, m dt over there, is negligible in front of the diffusive term. But I have to explain that, why. And so the problem is reduced to solve a simpler equation than the beginning one. But a simpler equation where you keep the nonlinear term. You see, in the preheated zone, you take out the nonlinear term, and you have a linear problem. Everybody knows how to solve. Now, the genius of this, of Zeldovich and Frank Kamiński, was to recognize that in the inner problem, the convective term is negligible in front of the diffusive term. So you have to solve this equation, and you will see that it is not difficult to find out what is the flux getting out from using this equation reduced. Now, why it is like that? It is because the term, I call that the convective term, m d theta over dx, is the order of magnitude is m delta theta divided by the thickness of the reaction zone. This is the order of magnitude. Okay? Now, if you look to what is the order of magnitude of the diffusion term, you are going to find that this term is yes, I did not see that here. Here it's clear. This term is delta theta divided by the length square thickness of the reaction zone multiplied by rho b dt, and you assume that the rho b is constant. That is the constant. Now, if you look more carefully, what was this reaction term here? It was equal to, but now you use the fact that the dt here, delta t here, is given, you know, wait a minute, 1 over beta. How do you find that? How do I find out? This is clear, d over dr. The d over dr here, this is rho u. Yes, rho u, d, yes, exactly. Now, this b is rho u ul. And now, again, d over dr, and this is 1 over beta. And And now when you compare the two quantities here, you have that one, they are equal, except because of that they differ only by the ratio dr over dl, and dr is small. So here you have, this is the same thing than this one, except that dr square here is dr over dl. Okay, so this one is much larger than this one because wait, I am dr square. Yeah. This term, because this is a second derivative. If it is a second derivative, is divided by the thickness of the reaction zone square. Okay. Here you see you have the same problem, exactly the same, divided by dr over dl. But dr square is much smaller than dr divided dl. So this term is much larger. This explains you why this term does not appear in the inner solution. So this okay. In order to go from here to here, I have used that M is called is the mass flux here is rho dt over dl, and the delta theta is 1 over beta. Okay, so now this term is negligible in for this term. So in the inner problem, you have to solve this diffusion, this equation. How to solve this equation? Very simple. You multiply by d theta over dx on both sides. When you multiply by d theta over dx on both sides, this on the left-hand side, you obtain the d over dx, d theta over dx square. Because you multiply by d theta over dx, if you derive this, you have 2 d theta over dx multiplied by d theta, the second derivative of theta divided by x. So this is this term, and now in this term here, you have this equation. Now you see the two sides of this equation here is a time derivative, is a space derivative d over dx. Now you integrate that over dx. So you integrate over x here. Let's see, and then on the right hand side you have to integrate. You multiply by dx and you integrate. You have to integrate this equation d theta. You have multiplied by d theta over dx. Okay, when you multiply by d theta over the what did I say? Yes. No, I say so. Excuse me, this is wrong. You multiply by dx, okay, and you have d theta, and you integrate. Okay, that's all. And here, to integrate this, you have the value of you integrate this. You have the value of the slope on one side minus the value of the slope on the other side, the exit. But on the burned gas, it is 0. So you find out that here you have the d theta over dx at the exit here of this side. And now the integration is a function of beta 1 minus theta, the integration of that, because I use the variable of integration of theta, and I have 1 over beta square, the beta square coming from here and here, and I have this two, and this you can, this equation is known, this solution. No. Now what you are doing to do, you say at the external, and this is a subtlety, at the external of this term is going to infinity, because beta is going to infinity, and theta now is out of 1 over beta, 1 over theta for the unity. So this is a key point. The key point is the following. It's very subtle. Huh? The key point is the following. Let me summarize the key points. The key point here. First of all, in the inner zone, the convective term is negligible in front of the diffusion term, and the ratio of the two is simply the ratio of the thickness of the reaction rate or reaction zone divided by the thickness, the total thickness, called DL here, of the external zone. So in that case, the problem that you have to solve is a problem of the type second derivative of a variable equal to a function of this variable, nonlinear function. The way to solve that is to multiply on the left-hand side by d theta over dx and multiply by dx and integrate. And on the other side, you just have to multiply by dx here and to integrate this. Okay? So this is a key point. Now you are going to match. So you know the expression of the flux. Upstream ahead of the reaction zone here, you have that you take the square root of that, okay? You have d theta over dx, and you obtain this here. This beta square is coming from here, and the fact that the integral of 0 infinity capital theta exponential minus capital theta d theta is equal to 1. This is a well-known result. So you know the expression of the flux going out from the reaction zone, and you know the flux coming in the preheated zone. You assume that both flux are equal, and you find out M equal this. And this tells you two things. That you see now, the rho B can be rho B UB. You find immediately rho B here, UB. M equal rho B UB, for example. So rho B UB, you simplify by rho B, you have UB here, which is square root of 2 over beta square divided by dt divided by T reaction, which is... And now you have the velocity, which is m divided by rho u, and this tells you that the ratio of the two is of order 1 over beta. This is an anticipation. Now you are going to verify at the end the approximation that you did to begin with. To begin with, I said, okay, the thickness is thin, but how thin it is? How thinner it is compared to the preheat zone? Here, the result is going here. It is 1 over beta. And you see now, these results are quite compatible with the dimensional analysis, except for terms like beta square. You say, oh, but this is important. Yes, but it is square root of beta square. It is beta. And this explains why you have a difference between this exact asymptotic analysis of Zeldovich and the order of magnitude analysis that I gave you just to begin with. And the ratio is beta, is factor 8. Oh, it's not so bad. And it turns out that when you compare this asymptotic result to numerics, you can solve the problem numerically. You find an excellent agreement. Excellent. Okay, here is a summary that flame is quasi-isobaric reaction diffusion wave. The flame velocity is highly sensitive to temperature. This is a key point. Because this is why because with beta going to infinity is to put this nonlinearity to the extreme nonlinear term. This is a genius of Zeldovich. And now you have here the flow velocity, the flame velocity relative to the burn gas. The reaction is here. So now if you divide by, and if you use that this diffusivity is A squared T cold, and then you use Arrhenius law, because this Arrhenius term, the square root of the Arrhenius term is still small, so this is a very small number. So the flame is markedly subsonic and is highly thermal sensitivity, the flame velocity. This is an important point for the following, that the flame velocity, laminar flame velocity, is highly sensitive to the temperature of the gas. This is an and now you can say, okay, yes, but when you have many reactions, you can do what you like, even with very many reactions. The flame velocity is very sensitive to temperature. In ordinary condition, you can find some condition where it is not the case. But to go further, I will give you some other results. This is old result by Zeldovich, okay? That you have summarized here. Now, you see, the non-dimensional equation that we have solved is this one, d tau, the dt minus the diffusivity, the nonlinear term W. So it turns out that at the same moment of Zeldovich was solving the problem of flame, Kolmogorov, another top scientist, was looking to another diffusion reaction problem. Same type of problem. Quite different result. Who is wrong, who is right? And I will explain you that. The main difference with a flame and the ordinary diffusion reaction diffusion flame is the nonlinearity in W in the term. What if you use a quadratic term, for example? Let me tell you that. What is the simple quadratic term? This is a quadratic term that is going 1 minus theta. It is a simple term. So what the problem of solved by there were three, in fact. Kolmogorov, Petrovskov, KPP. Kolmogorov, Petrovskov, Petrovsky. There were three very excellent math people interested in what they call the Fisher equation. The Fisher equation is this equation. Regard this. And theta is going to 0 to 1. Okay? So this is quadratic term. The other was exponential term. The nonlinearity was top nonlinearity. So I have just for you culture scientific culture. I show you different here, different case. For example, if this is the initial state, if the initial state is metastable or the initial state is unstable, the mathematical solution is quite different. Turns out that they were looking to this Fisher equation. And this Fisher equation was an equation that was developed to reproduce some problem in, how do you say it? Biological problem, physics, biological problem. It was used for the propagation of, it is not the nerve, because the nerve propagation, the impulsion of the nerves, electric impulsion of the nerves, in the nerves, you know, the goalkeeper and so on, would have a very short response time. But the response time is limited by the time of the electric pulse to propagate along the nerve. Okay. For example, if you put your hand on something hot, there is a delay for that. The delay is that the warmth that you feel hit has to be back to your brain, and this is limited by the time of the signal to propagate from your hand to your brain. And all these are governed. All these problems are governed by reaction diffusion equation, like that. But the main difference is that in this problem, in combustion, the problem is that the term is highly nonlinear. Here, the problem is the nonlinear term is weakly nonlinear. And I will focus my attention on the, I will not give you the detail, but for the unstable case, because the flame, in fact, is weakly unstable. You know, the flame is 0, 0. It's not metastable like that. And this is not true if you have, with multiple step chemistry, you can be in this metastable case. This is not so clear. So let's, now you look for, you know, you have this equation, and you look for front propagating at constant velocity, nu. And this is the same equation to solve that you have solved with Eldovich. But with the difference now that you cannot separate the preheat, let's say, there is no separation between the preheat and the reaction zone. This is the main problem, is the main thing. You see, here is a profile of theta is going to 0 to 1, and look at the reaction rate. It's occupied. It is all over the profile, not only limited to a thin zone. It turns out that this very good applied math, I will skip this because this is too technical for you. No, you are not interested in this. The problem is very, very interesting, but you are not interested in that. To solve this problem, people go to what they call the phase space to solve this problem. But I will skip this. And just, you know, here is the problem. You start with a bump. You are in the case of this case. You see, let me show you the one thing. Why the initial condition is unstable? Because in the initial condition, you have you are homogeneous. So you have this term, and theta is equal to 0. So you have just this theta. So you have and this is unstable. Okay? This is an unstable state. You have an exponential growth. It turns out when you have an unstable state, and when you look to the propagation of, an initial profile, you take an initial, this is a space here, and this is theta on the, here, on the vertical axis. So you start with a profile like that. And what is going to appear is that because of the reaction, you consume theta. So you are a wing propagating on the left, a wing propagating on the right. And you focus your attention on one of these wings and ask, what is the flame? Does there is a flame velocity, a propagation velocity constant for this wing? The answer is yes, there is one. But not exactly. There are many. So that when you look only to the steady state problem, you have many solutions with a minimum. This is the wave velocity, and this minimum, you have a continuous set of solutions with a minimum. And the one which is selected by the unsteady problem, because this one is an unsteady problem. This is a, well, I do not see anything without my glasses, so put my glasses on. So now, where is it? Yeah. Okay. Now, this is the equation, you see, assuming a steady state propagation to solve, okay? And this is steady state problem. And then you are looking for how many speed, mu, are getting out from this solution. Turns out that when you are unstable, like that, you have an infinite set of solution with a minimal velocity. It turns out, and this is the main result of Kolmogorov, is that when you look to the unsteady problem, the solution which is selected is a minimum. Is this one. This is to tell you in few words. I do not give you the advice to read the paper of Kolmogorov. Read the paper of Zeldovich, but the paper of Kolmogorov, you will have difficulty to read it. Forget about it. Just keep in mind the following: in that there is steady states like them, but because now you are strongly unstable in the initials, you are strongly unstable for theta close to 0. The formulation of the problem changed completely from a weak nonlinearity to a strong nonlinearity. And just to conclude, this is to show you that what we did, in '84. So we look to this to go continuously from this weak nonlinearity to this strong nonlinearity. It is also difficult to build and to see how the solution is changing. And it turns out that the lower bound here that you have changed completely of nature in such a way that when the sensitivity, when the nonlinearity become strong, this lower bound is no longer the solution obtained that you have here by Kolmogorov. It's quite different. And it is the one of Zeldovich and Frank Kamiński if you used this stiff problem. So this is just to show you that it's easy to understand why people did not understand the Zeldovich analysis. Because, let me tell you the story more. Zeldovich, Frank Kamineski solved this combustion problem, gave the answer. Kolmogorov, Petrovsky solved this Fisher equation, find a different, completely, and they do not talk each other. One has to wait 20 years that Zeldovich was saying, why? I have to understand how we go from this problem to my problem. And this is now clear, but this is just to sensibilize, to make you sensibiliser. What is that in English? I don't know. That to make you appreciate how a flame theory is a subtle thing. You see, a flame propagation problem is a subtle thing, very subtle. I try to present to you this theory without too much detail for you to make you understood. I am not sure that I have succeeded. But if you did not understand fully what I said, don't worry. The combustion community takes 20 years to understand Zeldovich. Okay, I hope that you will be better. Okay, thank you very much for your attention.